Section: Introduction. In this section, we discuss recent advancements in multimodal large language models, MLLMs, that have significantly improved their ability to handle complex reasoning tasks involving both text and images. For instance, models like GPT-4o have shown impressive performance on the massive multidiscipline multimodal understanding and reasoning (MMMU) benchmark, achieving an accuracy of 69.1% on college-level questions that combine these modalities. However, this raises an important question. Do these benchmark results truly indicate a deep understanding of various subjects, or are the models simply using subtle shortcuts and statistical patterns to find correct answers without real comprehension? This question is crucial for the future of AI systems in practical applications. If these models depend on superficial cues instead of genuine multimodal understanding, we might overestimate their abilities and risk deploying systems that could fail unexpectedly in new situations. To tackle this issue and enhance the evaluation of multimodal AI, we introduce MMMU-Pro, a more rigorous version of the MMMU benchmark. MMMU-Pro aims to better assess a model's true understanding and reasoning across various academic fields. The development of MMMU-Pro is based on several observations, such as the fact that some existing benchmark questions can be solved using text alone, the limited choices in multiple-choice formats, and the need to test models' ability to integrate different modalities more effectively. We created MMMU-Pro through a careful three-step process. First, we filtered out questions that could be answered by text-only models. Second, we expanded the answer options to make guessing less effective. And third, we introduced a vision-only input setting where models must answer questions based on images or screenshots. This vision-only setting is vital as it tests a key human skill, the ability to seamlessly switch between visual and textual information. It challenges models to truly see and read at the same time, similar to how humans process complex scenes with intertwined text and images. This skill is essential for tasks like interpreting scientific diagrams or navigating graphical user interfaces. Additionally, it reflects how users typically interact with AI, often sharing images rather than separating text and visuals. Our experiments show that MMMU-Pro provides a more thorough evaluation of multimodal models. We observed significant drops in performance across all tested models compared to the original MMMU benchmark, with declines ranging from 16.8% to 26.9%. These findings reveal the limitations of current models in genuine multimodal understanding and reasoning. We also found that while chain of thought, COT, prompting generally enhances performance, the improvements vary by model and context. Interestingly, explicit optical character recognition, OCR, prompts did not significantly boost performance for most models, indicating that advanced multimodal models have already developed strong text extraction skills from images. However, this also highlights that basic OCR is not enough for the challenges posed by MMMU-Pro's vision-only input. Our qualitative analysis further shows that when text is embedded in images, it adds complexity to the visual input, requiring models to recognize text, understand its context, and relate it to visual elements and the question. These insights not only provide a clearer picture of current multimodal AI capabilities but also emphasize the need for more advanced multimodal reasoning skills. We also revisit the MMMU benchmark, which is a comprehensive dataset designed to evaluate multimodal AI models on college-level tasks that require specific knowledge and reasoning. The MMMU consists of 11,500 carefully curated multimodal questions from college exams, quizzes, and textbooks, covering 6 core disciplines across 30 subjects and 183 subfields. Each question pairs an image with text and includes 4 multiple-choice options, featuring various image types like charts and diagrams. MMMU has quickly become a standard tool for assessing the capabilities of many leading multimodal models upon their release. However, we received feedback indicating that some text-only language models could accurately answer certain questions without visual input. Upon reviewing these questions, we identified 2 main issues. First, some questions are independent of the images. Second, even when images are necessary for human answers, models often find shortcuts or correlations in the answer options, using their pre-existing knowledge to arrive at the correct response. We illustrate this with examples that were correctly answered by Llama 3-70B Instruct. Section Summary. In this section, we discuss the advancements in multimodal large language models, MLLMs, and introduce MMMU-Pro, a refined benchmark aimed at rigorously evaluating true multimodal understanding and reasoning. Our findings reveal significant performance drops in current models when tested with MMMU-Pro, highlighting their limitations in genuinely integrating and comprehending visual and textual information. Section: Methods. In this section, we describe our methods for filtering and enhancing questions for our multimodal understanding model, MMMU-Pro. First, we filtered out questions that could be answered by text-only language models. We chose 4 robust open-source models: Llama 3-70B Instruct, Qwen 2-72B Instruct, YI 1.5-34B Chat, and MIXTRAL 8x22B Instruct. We tasked these models with answering questions from MMMU without any visual input, requiring them to respond even when they suggested that images were necessary. We repeated this process 10 times for each model, considering a question answerable if a model answered it correctly more than 5 times. We excluded any question that at least 3 out of the 4 models answered correctly most of the time. From the remaining questions, we randomly selected 1,800, evenly spread across 30 subjects, with 60 questions per subject. Next, we augmented the candidate options for each question. Even after filtering, some questions could still be answered by text-only models by picking up on subtle hints in the options. To address this, we increased the number of options from 4 to 10, making it harder for models to guess. Human experts, with help from GPT-4o, created these additional options and reviewed the original questions to ensure they were relevant to the images. This process eliminated 70 questions, leaving us with a total of 1,730 questions. These steps significantly reduced the accuracy of text-only models trying to guess the answers. To further challenge the models, we introduced a vision-only input setting in MMMU-Pro. In this setup, models received questions embedded in screenshots or photos, without any text input. Human annotators captured these images in a simulated environment, varying backgrounds, font styles, and sizes to reflect real-world conditions. This approach created diverse visual contexts, ensuring that models face challenges not only from integrating text and images but also from the variability in presentation. This mirrors how people often capture integrated visual textual content in everyday situations, enhancing the realism of our benchmark and pushing models to better understand multimodal tasks. After these steps, we ended up with a total of 3,460 questions, split evenly between standard format and vision-only format. For our experimental setups, we established baselines to understand MMMU-Pro's difficulty and provide reference points for future research. We evaluated a variety of state-of-the-art multimodal models, including proprietary models like GPT-4o and Claude 3.5 Sonnet, as well as open-source models like Intern VL2 and LLAVA. We assessed these models across 3 settings: the standard setting without augmented options, the standard setting with augmented options, and the vision-only input setting. The overall performance score for MMMU-Pro is the average of scores from the augmented and vision-only settings. We also included the original MMMU validation set performance for comparison, highlighting the increased difficulty of MMMU-Pro. We evaluated the models using both direct and chain-of-thought prompts, reporting the higher scores in our results. Section Summary. In this section, we filtered questions to exclude those answerable by text-only LLMs, augmented candidate options to increase difficulty, and introduced a vision-only input setting to better reflect real-world usage patterns. After these steps, we compiled a total of 3,460 questions and established a diverse set of multimodal model baselines to evaluate the challenges presented by the MMMU-Pro benchmark. Section: Overall results. In this section, we present the overall results of our MMMU-Pro evaluation across different models. We observed that increasing the number of candidate options from 4 to 10 led to a notable decline in performance for all models. For example, GPT-4o-0513 saw a drop of 10.7%, going from 64.7% to 54.0%. This suggests that having more options makes it harder for models to guess the correct answer, requiring them to engage more thoroughly with the multimodal content. When we introduced a vision-only input setting, we noticed an additional decrease in performance. For instance, GPT-4o-0513 dropped another 4.3% in accuracy, while LLAVA1 Vision 72B experienced a significant 14.0% decline. This indicates that the vision-only setting effectively tests the model's ability to combine visual and textual information, revealing their limitations when text is not provided. The overall difference between MMMU-Pro and the original benchmark showed a significant decrease in accuracy across all models. For example, Gemini 1.5 Pro, 0801, and Claude 3.5 Sonnet had declines of 18.9% and 16.8%, respectively, while VILA 1.5 to 40B faced a drastic 26.9% drop. This suggests that MMMU-Pro effectively reduces the shortcuts and guessing strategies that models might use in the original benchmark. We also explored whether optical character recognition (OCR) prompts could enhance performance in the vision input setting. However, we found that including OCR prompts did not significantly change performance. This indicates that capable models are already good at extracting and understanding text from images without explicit OCR prompts. It highlights that simple OCR is not enough to tackle the complexities of the vision-only input, as models must understand the context and relevance of the text within the image. Next, we examined the impact of chain of thought (COT) prompting on model performance in both standard and vision input settings. Generally, COT prompts improved performance, but the extent varied among models. For instance, Claude 3.5 Sonnet improved significantly in the standard setting, while LLAVA1 Vision 72B showed minimal gains. Some models, like VILA 1.5 to 40B, even experienced performance drops, likely due to difficulties in following instructions accurately. This emphasizes the need for strong instruction following capabilities for effective COT implementation. To gain deeper insights, we conducted a qualitative analysis of MMMU-Pro results, focusing on 2 scenarios: correct answers with 4 options but failures with 10, and success in the 10-option setting but failure in the vision input. We identified key factors affecting performance, such as challenges with increased options, where models often chose the closest answer rather than a definitive one, leading to errors. Additionally, the integration of text and images increased complexity, causing models to hallucinate or reason incorrectly. These findings highlight the limitations of current multimodal models and point to areas for improvement, such as better handling of multi-option scenarios and improved integration of visual and textual information.